I'm Si-Hui Tan. I'm the Chief Science Officer of Horizon Quantum Computing. So we
Wow.
are we are a quantum software company that's headquartered in Singapore, and I mean the mission is basically to try to make quantum computing available for everybody and allow people without quantum knowledge to be able to run quantum programs on quantum computers.
So quantum computing is relatively new to most of us. But I hear the term more and more, quantum computing, quantum technologies. And it's really interesting to become aware that people have been working in this industry for a while. So what's been your journey to getting to Horizon?
Gosh, I started with a passion for physics, really, and when I was a kid, astronomy to be specific. So it's quite different from quantum computing. But as things progresses, I went to college and I studied physics. I was looking into maybe doing a PhD in the same, in physics. And when I was like just getting out of college, I asked around, my advisors, my seniors, what's the interesting thing to work on, right? And quantum computing came onto my radar from one of the seniors who is also a very prominent, she's a very prominent quantum physicist, Dr. Debbie Leong, or Professor Debbie Leong. And she was a senior at my college at Caltech. And she had been working on quantum computing and said, this is what it is and like what she's been working on. And I said, oh my goodness, that's so cool. And then I started looking into maybe doing a research project in quantum computing for my senior year project. Not really a thesis, but just to look at it for a special course. And then I got hooked.
And so what do you do specifically at Horizon?
Well, so what I do at Horizon, oh, what we do at Horizon, is basically, I guess that's the mission, and then that's what we're trying to build. So, what happened was that, around 2018 and sometime before that, we were starting to see a lot of interest in industry, right? Trying to get into quantum computing. And then hardware started, like, the qubits got better, like the quantum bit got better. Some systems came online, so notably IBM in 2016 or 17, around that time. You start to be able to just, go onto the IBM quantum site and then like get access to the quantum computer and actually run it. You might have to wait a little while, but you can do that. But we started to feel like, I was then a postdoc in the university and working on quantum computing. And then we started so my boss and I, so my postdoc supervisor Joe Fitzsimons and I, we found that there really to make quantum computing useful, there's a lot of like barriers, and one of them is hardware for sure. But then the other is that software. There's really the algorithms behind making quantum computers work, finding applications for it. There's really a gap in making quantum computers useful, even if it's available or it's becoming available. So then we decided that it's going to be like the university is not really the place to get that to work, like to try to do something useful and contribute to making quantum computing useful. So Joe founded the company Horizon Quantum Computing, and I joined as the chief science officer, and this was back in 2018. And boy, it was a journey. It's like been 4 years. Uh,
Which in the
yeah.
grand scheme of things isn't really that long.
No, no, but I guess the last few years been really long. Yes, but it's also like a journey to to try to build something rather than just doing research in the area. Of course, research is part of it. I mean, quantum computing, as you mentioned before, is still relatively young, and there are a lot of open questions. but the consensus we had, at least, and I think a lot of people in the area, the research area, feels that, we need to find the application that would make quantum computing useful, because, but just the amount of work that has gone into progressing the hardware and stuff, it's just truly tremendous right now to see that progression. I remember when I was, when I just started getting interested in quantum computing, 7 qubits was a big deal. And at the time, I think this is, gosh, I'm going to review my age, right? So it's 2003 or 4. And it was just incredible to see now that, you could have 53 qubits, 127, and upwards of there, right? Like, so it's truly incredible. But of course, to have, like the little pieces come together, we still need quite a bit more to patch. Okay, so what is the useful thing we can do, right? So of course you think of Shor's factorization that basically breaks RSA. You need probably millions of qubits and very good gates. You need fault tolerance. All these pieces have to come together. But of course, then there's the potential of maybe there's something in between, right? Like where you have relatively large systems that can outperform, that can do calculations that outperform quickly enough that outperforms classical computers. But it's, not quite like, for example, the Google quantum supremacy experiments, right? But it's not quite something that, can do something useful for you. It's not like you can get it to tell you, the weather predictions for tomorrow, right? So it's not, so to speak, a useful application of quantum computers, but they can outperform. We know that, whatever they're doing, well, or at least we believe strongly that whatever they're doing is done more quickly, a lot more quickly than classical computers. But really to look into that niche where it's like, well, is there something more we can do, right, in this regime? But that's one of the, but to create algorithms is difficult, right? Even for classical algorithms, it's really difficult. But quantum algorithms, you need quantum mechanics, you need computer science. So what we're trying to do at Horizon is basically to try to find the pieces that you need to be able to say, somebody coming in with metrology knowledge and they want to use quantum computers to see if they can tackle a very difficult calculation. And oftentimes they come in with no quantum knowledge, though maybe that will change a little bit with time now, since more people are getting involved in doing computations, and not just in quantum computing, but in like supercomputing, large scale computing, basically high performance computing. So if you think about it that way, if they come in with domain knowledge, but they need some time to learn quantum computing, how to fit their programs onto the quantum chip, and run the algorithms and then figure out how it can be sped up. It does take some time. So what we're trying to do is to figure out, the little primitives that you can do to be able to recognize where in a piece of code can you figure out that you can be sped up by quantum computers by applying the techniques that we know will work on pieces of math, or things like repetition in loops and things, and try to compile that, and then from there compile that down into quantum circuits, and then fitting it onto a chip, and then so on and so forth. So it's really a compilation stack that we're trying to build to be able to do that.
Do you know what? I actually get what you mean, which is quite amazing, because
That's awesome.
quantum computing is so complex. I mean, I must say that I've been quite bogged down by the quantum mechanics and quantum physics of this story, because, when you've got things like entanglement and superposition and like all these different amazing phenomena, you can go down a rabbit's hole with that. But what you are bringing us up to speed with is the fact that where we are with quantum computing is that we're trying to figure out how best quantum computing can help us. And it doesn't necessarily mean that quantum computers will figure the whole answer to a massive question. Where we seem to be is that quantum computers can be used today to take parts of a question and work on those little parts so that we can piece it all together in one giant jigsaw of an answer. Is that where we're at?
That is what we are working on at Horizon. I think it's an approach to using quantum computers, and you're absolutely right. I actually personally believe that it's not necessarily that you would like to have quantum computers. If you look at a problem, right? For example, in the extreme case, like finding the Higgs particle, right? So I have friends in high energy physics who do calculations and predictions, and you get a ton of data too coming from that, right? So the modeling, the predictions, the analysis, the results, and storing the results, and all of that. But like to speed up, like what part of the problem do you want to do, right? Like and if you it might be a small gadget of a small part of a computation. It might, quantum computers might be good at speeding up, but maybe not other things, right? Like I think it's classical computers are really good at some things, and you probably would not be able to get quantum computers to speed up something that a classical, or you don't want to because it's so expensive, right?
Mm.
But if you could harness that entanglement to do a particular piece of computation, right? I can't, off the top of my head, I can't find a good example right now, but it's that it doesn't have to be big, right? It could be like linear algebra in like optimization, or even a small subroutine, right? In an aerospace modeling simulation. So it's a lot of ground to cover, but there's also the advantage of having a lot of people out there who have been doing high performance computing, and being very entrenched in like speeding up certain types of calculations. And I think if we start to think of quantum computers as a form of high performance computing, then we start to get beyond the fact that, oh, it's so strange and so weird. Because I think from the way things are like moving along right now, you're starting to not have to worry so much about, well, not yet, we're not yet at the point, but we hope that by building this compiler that we'll get to a point where you don't have to think about, how do you fit things onto a chip. I guess actually even now, like a lot of the hardware companies have low-level languages that lets you do that already. So, but you still need to know, okay, what is it that you want to do here? Is it, this gate, that gate? Do you need entanglement here? How can you build Grover, for example? Or so there are all these little pieces, but we like to draw parallel to the progression of classical computing. And if we just think about 1950s or 60s when the first computers came about, right? And those were like really big computers, and you have to use punch cards to like encode information onto a tape, and then if you make an error, then the people working on the program has to like wind it back and, oh, where's the error, here it is, and then like go back and repunch it, right? So it's like super weird to think about it that way, whereas now you can pull up Python and just learn it in 2 weeks and then start playing around with it because there's a whole suite of tools out there that are already there to help you progress in your problem. So I think we're trying to get quantum computers, at least, to that, like we are at Horizon, to try to get it to that stage where, we could have a language where you can just type out what you want quantum computers to do, and then you can be able to synthesize the algorithms and have it compile down into a quantum circuit.
Right. So you're basically the middle man, middle person, to be gender non-conforming, that is bringing the hardware and the application together by compiling all the different steps in between.
I think that's a good way to summarize it. There are a few things we like to think we're going to do at that point. Things like optimizing the circuit, playing, figuring out if you can reduce the gate counts, the resources you need to build the circuit you want. But yeah, pretty much, like automatic algorithms, quantum algorithm synthesis, um, routing, figuring out, if you can optimize the circuit, reduce the gate counts, um, to be able to push that boundary forward.
One burning question that I have is, does the average person need to actually know about quantum computing, or should we just stay blissfully unaware that computing is massively advancing thanks to quantum technologies?
That's a very good question. I think I'm always curious and I always want to know. But yeah, I think you probably don't have to know quantum mechanics. Though I think maybe it could be interesting if you want to learn it. Uh,
No, the reason why I ask is because I've never asked these questions about classical computing. Like, I've never asked about how software relates to hardware. I don't actually really know. I mean, I know everything's binary in classical computing, but beyond that, like the ones and the zeros, I don't really know how computers work. So I wonder why I'm even doing this quantum series, because I mean, I'm doing it because I find it really fascinating that computing is going in a different direction, because quantum computing is nothing like classical computing. But it's so complex that I wonder whether the average person should just remain unaware and just enjoy the fact that computers will get really powerful as a result. Like, you know, do we actually need to know that quantum computing is becoming a thing? Because it's not like, I mean, put another way, I guess my question would be, is quantum computing actually ever going to become part of our daily lives, or will it always be in the background doing all the number crunching?
I suspect at least for a very long time, it's going to be a high performance computing tool. So in that sense, it's a very specialized tool. I don't. I mean, I should say this on tape, but I think, but at least for the foreseeable future, I think it's going to be probably on the cloud, for use special purpose computation. Uh, and I think in a way you're right. I think the world will go on if you don't know quantum mechanics, if you don't know quantum computing. Um, so yeah, I also have to admit, I think, starting out as a physicist, I had to learn a lot of that, computer architecture, computer hardware, stuff when I, moved to quantum computing and learning about quantum computing. And that was actually, for me, the hardest part because, when I was at Caltech and MIT when I did my schooling. I was really into, well, at least the earlier part, I was really into just, physical phenomenon, learning about, um, material, electromagnetism, the universe, cosmology. Um, so, like when you have to look at how information theory works, it's itself a fascinating topic, but very different from physics. Um, but as you say, there's a rabbit hole, and as as when you look into the quantum mechanics rabbit hole, you can also look down the information theory rabbit hole. And there's a huge, long, fascinating history, though it might not be as old as physics. So I think of the father of information theory is Shannon. That was in 1950s, where he and other people, of course, Alan Turing and others, like came out with the theory of like how computing should be, how we can encode information, and perhaps in some ways be able to encode a lot of things into like this Turing model way of computing and thinking about things. But for me, that's also a steep learning curve, and I don't think it's unfair to say that probably the world will keep going on even if you don't know all of these things.
Yeah, I mean, there are a lot of quantum mechanics to decode. I mean, to really try and wrap our heads around. But I think because I'm talking to you and you're based in industry, I think what will affect us the most about the work you're doing is the fact that certain aspects of computing will hopefully be taken over by quantum computing, which will mean that things will get speeded up. We'll be able to ask more complex questions. Which industries do you think will be most affected by this technology, and when?
Oh gosh. And when, okay, so I think I've alluded to it a little bit. So it's I think oftentimes when we think of what applications quantum computers have, it's basically limited by the availability of the algorithm for the type of problem you are solving. And largely, the big known algorithms can be classified into, three or four kinds. Of course, there's like different models of computing and, you know, uh, but for computing all purpose, no, of course, and then there's cryptanalysis, like like breaking crypto systems, and that's like the key distribution. That's a whole new different ball game. Like there's a lot of algorithms there too. But in terms of computing and having primitives or speed ups, there's of course the more recently there's the HHL algorithm, which is for machine learning. There is Shor's factorization, which is period finding, primitive quantum Fourier transforms, phase estimation, and then there's Grover algorithm, which is for search. So, and each of these classes have like their own expected speedups, and people have been trying to get better speedups over classical computers. But largely, you can really count with maybe 10 fingers, like the like your hands, right? On your fingers, like how many algorithms there are. So we think that actually there might be more, but it's just the type of people that are drawn to those problems. They like solving certain problems, and when you start out, of course, the most mathematical people are in cryptanalysis, right? Because that's a highly mathematical area. And and then it comes, even when you look back to like classical computing, like a lot of the breakthroughs that happened for computing happened because we needed to break. Well, I wasn't there, but humankind needed to break the Enigma machine, right? And
Yeah.
so
And security.
yeah, the security of a particular crypto system. And but later on, then you start to see that actually the techniques that were used to compute could actually also be applied to other types of problems. And now we're just seeing like amazing stuff. Like I mean, like CGI for Interstellar, right? Like whoa, okay. But then also, of course, landing on the moon and other things like that, and having Voyager, the um, I forgot what the name of it is, the satellite that went out of the solar system, and having to encode information and decode it, and stuff like that. So I mean, it's all this stuff was incredible, right? But when we started out with computing, that wasn't what we envisioned. Maybe that wasn't the initial intent, but it's sort of gotten its own life. And I think in some ways, we hope that this is going to happen with quantum computing. But coming back to your question, like what do I think, will benefit from quantum computing? I think a lot of the mathematical problems, like the areas where there are hard mathematical problems, I think that's the first natural place to apply them to. Um, so I guess if I need to put more specifics on it, it's like, bank, like finance, weather modeling, uh, aerospace, pharma, where a lot of computing power, or even like, I think there's this potential for, yeah, pharma, but there's also, I forgot. So chemicals, like finding the right chemicals with the right characteristics. Uh, so all these things, all these areas, they use a lot of computing power.
Yeah. I mean,
Yeah.
it is exciting to think that we're developing quantum technologies with certain ideas in mind, but that will lead to other technologies which we haven't even thought of yet. I mean, when you talked about machine learning, I mean, that just opens up a whole other can of possibilities. And so, it's a case of actually watch this space. And, hearing you talk about that actually gives me conviction that it is important to understand quantum computing at its basic levels, because it sounds like it's going to be so woven into the fabric of society in the future. So it is important to have some sort of base knowledge. But with all of those kind of ideas, hypothetical ideas, does it all hinge on the number of qubits? And if so, like, where are we at today with that?
Yeah, so I think the number of qubits certainly is one metric that we go by, though it's not the whole story. Uh, you know, the reason the reason okay, so a certain another metric that we need to worry about is really the quality of the qubits and the type of gates that you're performing. So it's about the interaction between the different qubits, which is essentially what is what is doing the entanglement and allowing you to get the speed up that you are looking for. So it's also, once you start to scale up the number of qubits, you start to worry about error correction, because if you don't, without error correction, which is a big bottleneck for quantum computing, which is that when you start to have more qubits, of course, because they're so tiny and sensitive to noise, you expect the amount of noise to go up, right? Without error correction, you start to get this drowning of the information in that noise, because you have so many qubits. Without error correction, that is going to be the case. But if you do have error correction, then you can start to suppress that noise as you grow the size of the QPUs, the chips and everything. So it's, a number of qubits certainly is important, and with more qubits, with more good qubits, you can have error correction. But you need both.
That error correction is actually handled by qubits as well, right?
Yeah, it's true entanglement and a very clever encoding where you could actually, because when you, one thing about qubits is that when you start to measure them, the way, at least in the way that we measure them now, you destroy them. Actually, not destroy them, but you actually disturb the information that's being stored in the qubits. So to do error correction, you need to have extra qubits, and then you, depending on which code you use, you could correct certain types of errors. Hopefully all errors, but and then when you start to measure, you do syndrome measure, you can detect the error. You can try to detect the error, which is called syndrome measurement. The syndrome is like the error syndrome. So what is the error? And then you can try to correct it. But then, because when you read the qubit, you would, destroy the information that's stored within it, that's in it. You have to then use entanglement with extra qubits and then do it in a way that you're not actually destroying the information while you're trying to detect and correct the error. So that whole area is fascinating, and I can't say to be an expert at it. So, but I do, I did learn about it, and I followed the news recently, and it was just a particular type of error correcting code. It's called a surface code, and it was just recently last year that was demonstrated by a group, by two groups almost simultaneously. ETH and so Andreas Wadroff in ETH and Jianwei Pan's group at Hefei in China. So uh, that was fascinating. And then of course shortly after, Google had a another experiment where they showed that not only that they demonstrated the surface code, but they also showed that as they grow the size of the number of qubits in the code, the error did not blow up. So in that way, they were able to suppress the errors even when they grew the size of the code.
So what kind of breakthroughs are we hoping for? Like, what are we on the verge of in terms of breakthroughs? Like, what would really help to make us feel that we've reached a milestone with this?
I think we have to remember that all these achievements that I listed, they were really great milestones already. But I think if we could, if Google, like that last error correcting code experiment, if it could go further and have more data points on that line, I think that would be truly stupendous. Um, and of course, I think if we start to see scalability in I think I forgot to answer one of your questions, which is how many qubits do we have now, right? So I think so that's question of what is in development and what is actually commercially available. So I'm probably behind time now, but I think IBM has 127 qubits processor, but they were talking about I think 400 plus this year. So if you look at the roadmap, uh, you know, and I think one of the key things is that can you have two chips talking to each other coherently? So in the quantum superposition or quantum entanglement, but without a lot of like extra noise. So that would be another achievement, I think, because then it's easy to see how you could scale it up. So those two things I think would be great as well. It's like a Christmas wish list for a quantum
Yeah.
computer scientists.
I mean, is there any sort of like big names we should be monitoring? You know, I'm just imagining a whole bunch of quantum computer engineers kind of all working towards this day when X happens. Like, what is that X?
It's fascinating, isn't it? Like, what is the point? What's the end point? What's the end game? I don't think anybody really knows. I think we are all, at least in the community, we all have like this problem that we're trying to solve. And I can say at least for myself, like, that's like that takes up all my time right now. So, but I think there's another group working, the other groups working on the hardware, the connectivity, a different type of architect, a different type of quantum computers, right? Like a different implementation. So, you have different ways of manifesting a qubit or manifesting a C naught gate of doing different types of surface, like error correcting codes, right? Then you need new codes and things like that. So there's a lot of interesting work. I can't think to say of any one name that we need to look at. Of course, there's always like somebody that you look up to, right? Like when I was a student, like Praskill or my supervisor Steph Lloyd, like it's incredible. But I think we're starting to see. I think this is only testament to say how many more people are starting to jump in now to try to build something useful. And I think it's not just like the people, the founding fathers of quantum computing that you look up to now, but it's like, okay, really, like now that we know roughly what it's capable of, like the boundaries of the space. I shouldn't say boundary, but at least the minimum the minimum that it might be able to achieve.
Framework.
Yeah, the yeah, like what that it could be possible, right? Then there are a lot of non-physicsy things that you could do, that you want to realize, try out, like heuristics, right? What are the heuristics that will allow better computing, quantum computing? What are the things that is possible, and sometimes we forget that people working very focusedly on one problem. So all the researchers out there, it's like it's often the case that you forget to talk to another group of people. Uh, and I think just being able to have a platform, an ecosystem where people can chime in and share things, like at conferences, like at being a conference, I think that will help push the field forward. But just right now, I don't think there's so many different problems to solve, so many barriers to overcome. I don't really think there's really one thing or one person I can say that will truly bring this to that will change everything. It's not like a theorem with an unsolved proof, like a conjecture with an unsolved proof, or but yeah.
I mean, in listening to you, it's clear that there are academics, there are people from industry, there are commercial interests. Like there's all these different perspectives, all working together to make quantum computing a reality. And they're all rising up with time. And there's also people in the media like me who want to try and summarize it in basic terms. And I still think it's not unfair to say that the advancement of quantum computing is very much about qubits. That would be like the basic statement, the summary statement. And then around that is, how do you create those qubits? You talked about all these different techniques, and I've heard many times about, superconducting, photonic, like all these different ways. But I guess, it's an exciting prospect to think that we are tackling quantum computing or computing. We're tackling computing in a very refreshing new way, and it promises to be really powerful. I think one of the burning questions I had, which is slightly off topic, is just how inspiring it is to listen to a woman who's got a background in physics, and is moving into quantum, and then also being supervised and working with a very, very esteemed woman again in the same field. I mean, how is it a research field that has gender balance? Because that's never been the case in physics.
It's very interesting you should ask that. I didn't realize how special. I think in a way, yes, quantum computing has a privileged position in that I think there are, because it's such a young field, and such an interdisciplinary field. I have noticed a larger percentage of women around me in this field. And I don't know exactly why. I could conjecture. I really conjecture. I said it's a young field, and I think that's the reason. Because with with open, when you move away from a traditional area of physics to something as new as quantum computing, it takes a certain amount of like open-mindedness to to accept that maybe this is going to be a thing in the future. So with that open-mindedness, maybe there comes a certain acceptance that people will be different from you. Um, but yeah, I have I can say there could still be more women, but it's pretty amazing that I had a lot of good women mentors in this field. And actually, and also not just women in the field, but women who are very passionate about what they're doing, very capable, very awesome, like top-notch physicists and computer scientists. And there's a Facebook group for quantum, like women in quantum computing science. And I think that is a source of a lot of good advice and very well-meaning advice throughout the years. Um, so it might be special for quantum computing, but hopefully not for long. Hopefully other areas in STEAM would catch up.
Yeah, I mean, what's the Facebook group if anyone wants to search for it?
Oh, it's not an open group, but it's called Alice. Alice in Quantum Information, I think is the name.
So
Uh,
it's like
yeah.
ALICE.
Yeah, so I don't know if you know the background for Alice and Bob. So one of the first applications of quantum computing, it's not really computing, but it's key distribution, right? So in key distribution, so it's basically about creating a secret key that is shared between two parties, and that there are protocols to extend it to more. So you can use that in encryption protocols as a secret key. So in those protocols the two parties are usually called Alice and Bob. So yeah, so when you say Alice, and it's funny. I don't know. I have a weird sense of humor.
That's like a perfect geek joke, where only people in the know will get it. Thanks for shedding some light on that, because I have actually heard about Alice and Bob before, but it's completely gone over my head because I've had no clue. So that's
No, it's just a protagonist in because in okay, so here's the thing about quantum information, right? So because there's so many different types of people in it, you learn about different practices, and so gosh, I'm going to say this openly, and then computer science is going to email me. So in computer science, unlike physics, I think it's when you write the proceedings in journals. Uh, or papers, you are very systematic about what you mean in your protocols. So to the point of being pedantic. So it's like, the step one, two, 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 three, what is the prior knowledge and things like that. We do that in physics too. It's just maybe a lot less like like it's a lot more like reading a storybook rather than going through the history of things. So it's quite a different style of writing publications. There are also other things like, for computer scientists, usually proceedings and conferences are more prestigious than publications, whereas for physicists, proceedings don't really matter. There are like cultural differences in these different areas. So when you talk about Alice and Bob, they're really, I think for me, it's just two names for names for protagonists of your protocol, and an easy way to relate to whenever you say, you don't have to say, oh, let's call this person A and call this person B. It's just Alice and Bob. And every time you say Alice and Bob, you infer that they're protagonists in participating in some kind of exchange protocol.
wow. Well, You know, it's incredible that you span so many different disciplines and that you're bringing all of your expertise and knowledge into the world of quantum computing, and you're really pushing the frontiers of this field forward. It's been really inspiring to speak with you. You know, I can't claim to really have a sort of thorough knowledge of some of the things you've mentioned, but what has been so enlightening is how what you're doing fits into the bigger picture. Because even if I don't understand things fully, I think it's so important to have an appreciation of where technology is heading, because I don't think our future will not involve quantum in a significant way. So you've really shed a light on everything. You're so inspiring and so impressive in all the things that you've been doing. So thank you for taking the time out to share with us your expertise, but also give us a little, you've given us a real sort of like peek into the world of quantum, like in a very human way. I love this Alice and Bob idea. I don't feel like I'm part of the club, and I'm sure it would take a lot to even join a Facebook group. Probably, absolutely, I wouldn't be able to. But
But thank you for having me. I mean, it's such a pleasure to talk to somebody who's so passionate about, learning about science and like culture and everything. So it's such a pleasure to talk to you. But yeah, I would say don't be a stranger. Just, I think if you want to talk to physicists and women in physics, go to a physics conference. I'm sure you can just, go there and talk to people. And I think at least for quantum computing, a lot of the people I know are very open about talking to not like non-physicists basically.
yeah,
So I think yeah.
and it's really great that you do talk with non-experts, because everyone has curiosity, right? And you took your curiosity through to your career, and I hope many women and men and everybody in between follows in your footsteps, because we definitely need more experts in this field. And I think in order to get more experts in this field, we need to spark their interest and keep their curiosity going. So you've done that for us today. So thank you.
Thank you.